Okay, so I just wanted to go through a couple of things on StatCrunch to help us in constructing confidence intervals. Uh, if we go, so the first thing was we're just going to take a look at how to find critical values, right, for any level, but in particular ones that the empirical rule doesn't help with. So I'm going to go to Stat Calculators Normal, same place we've been going. So critical values deal with the middle area. So I'll click between. It's already got the standard normal pictured where the mean is 0, standard deviation is 1. So this is a distribution where along the x-axis we have z-scores. And then the confidence level is the same as the middle area we want. So for example, the 95% confidence level would require us to have a middle area of 0.95. And we click compute. That gives us our z star that I used in the examples of 1.96. Very close to 2 from the empirical rule. If we wanted the middle 99.7%, too many nines, input 0.997, get very close to 3, about 2.97 there. One of the levels that I used in the example was a 99% confidence level. That's a middle 0.99 area. So 2.5758. I think I rounded to 2.576. And then finally, I did one for 97% confidence. And that goes from a little bit over 2 to the negative of a little bit over 2. So minus 2.17 to 2.17. All right, so you can do any confidence level you wish. Just make sure you use the between feature so you're getting to the middle area and not a left area when you're finding that critical value. Now I also wanted to take a look at a simulation that kind of illustrates that when we say we're 95% sure, right, for a 95% confidence level, that our interval really does contain the true unknown mean or proportion, that really is 95%, right? So there is a 5% chance that your interval does not include the thing you're trying to estimate. And there's a simulation on StatCrunch that helps display that. So if I go to Applet's confidence intervals for a mean, the setup's a little bit, it's got more to it than we really need at the moment. You can ignore a lot of this. I just wanted to make sure I clicked population standard deviation sigma. So this is a z, that's standard normal, where we know the sigma. We're sampling from a normal population where the mean is 50, standard deviation is 10. And so this is one where we know the mean to be 50, but we're going to simulate taking 100 different simple random samples from the population, finding 100 different x-bar estimates for the mean of 50, forming 95% confidence intervals for all 100 samples, and then we check to see how many of those really captured the true mean of 50. All right, so we hit compute. And this graph displays all 100 confidence intervals. The green dots are the sample means, and then the intervals extend to sample mean minus margin of error to sample mean plus margin of error. And out of this batch of 100 randomly chosen samples, notice that we've got 4 that are red. And that's because these 4 confidence intervals did not capture the true mean. So this first one, if you hover over it, well, yours will be different because they're random. It goes from 34.7 to about 47.1, but the true mean was 50. So this confidence interval failed to be a good estimate for the true mean. This one again, this one goes 36.6 to 48.9. It doesn't get all the way to 50. This next one barely missed, 50.2 to 62.6, but it missed on the high side, and this one was a little bit worse. So that's 4 out of 100, or 4% of the intervals out of that simulation failed to capture the true mean. So that, right, we only did 100 intervals, So we wouldn't expect necessarily to get exactly 5%, but we could redo it. And out of this batch of 100, we missed 1, 2, 3, 4, 5, 6 times. So on average, right, we're missing about 5 out of 100 times. Right? So that is what the confidence level really means. That if it's a 95% confidence level, that really means you can only be 95% sure that your interval includes the true unknown population parameter. And that is all I wanted to do for this video. I think that concludes.